Welcome everyone to our next TDS webinar, and this is my great pleasure to introduce Tomas Vyhlidal, who is from the Czech Technical University, Prague, and he has been doing very substantial work on the area of time delay systems, in particular its relationship to robotics and cybernetics. So the applications are really cool. I think I met you maybe about 12 years ago in Stanford in one of the conferences. I still remember that was a really nice meeting, and we had some good discussions. And since then, I have been following what you've been doing, and it's very exciting. So thank you very much for accepting the invitation. And without any further ado, the floor is yours.
Okay, Gabor, thank you very much for the introduction. Let me also thank you and Wim and other organizers of this webinar. It's a big honor to give a talk after those big names of the field. Yeah, so. Hello, everybody. Good morning, afternoon, and or evening, depending on your time zone. So today I will talk about time delay algorithms, and particularly their application to vibration suppression. Yeah, so there will be a bit of theory, and I will focus on applications. When preparing my presentation, initially I had too many slides. Even now I have quite many, close to 60. So I try to remove equations. Yes, but I always put references to literature where you can find some more on the topic. Yeah. So. As Gabor mentioned, I'm from the Faculty of Mechanical Engineering in Czech Technical University in Prague, and I also have a research group in the Czech Institute of Informatics, Robotics, and Cybernetics, which is a research institute. And of course, what you will see, it's not only my work. Yeah, so I will thank at the end to all of my key collaborators, and there are plenty of them from the department as well as from abroad. Yeah, so in my talk I will very briefly mention spectral properties of time delay systems, because in the synthesis of our algorithms we use this approach. So we use spectral and frequency domain synthesis. Then a large part of my presentation will be devoted to delayed resonator, some recent results, mainly also the a bit theoretical results, but mainly you will see the experimental validation. And very similar topic to this one is periodic disturbance compensation, where we can meet quite a bit more complex periodic functions. Usually we use repetitive control, and together with my colleagues we have proposed some alternative using internal model control. And at the end, hope I will have some time, I will say a bit about input shaping, which is actually the first topic in vibration suppression or flexible mode compensation I started to apply I started to work in. Okay, so very briefly, I think all of you are aware of spectral properties and system definition of time delay systems. So here I have a couple, several monographs on spectral and frequency domain synthesis, starting from the book of Bellman and Cook, of course, work by Komanovsky, Mishkis, Hale and Linnell, Silviu Niculescu, Gu Karitonov Chen, Wim Michels, and again Silviu. These are my favorites. Of course, there are plenty of others. I see Emilia Friedman here. She has also a very nice book recently or published, but it's on Lyapunov methods. So this is not my main topic. As I mentioned, we use frequency domain and spectral domain. Yeah. So in the design, we use linear time delay systems, usually in this lump delay form. But you will see that I also use distributed delay. Then the equation is a bit more complex. We need to use Stieltjes integrals, but structurally is very similar. Yeah. So this is a general description of a time delay system. So next to the delays in the states and in the inputs, we can have delays also in the state derivative. Yeah. So if this happens, we have a neutral system. Otherwise, we have a retarded system. Yeah. The stability can be determined using the spectrum distribution. A typical feature of a time delay system is that we have infinitely many roots, and to have the system stable, they all need to be located to the left of the complex plane. Yeah, if we look to the time domain, a typical feature of state of time delay system is that the system state is not given at a time point, but it's distributed over a time segment history. Okay, so once we have a neutral system, which can happen even in even in engineering applications. Yeah, so we can arrive to neutral. Yeah, even in engineering applications, we can come to a neutral system, which has the delays in the derivative part, as I have mentioned. Yeah, so in this case, we also need to look at the associated difference equation, which is here, which is basically different by the left-hand side, and to its root distribution. Neutral system have very peculiar feature, and one of them is that a part of the spectrum is distributed in parallel sectors of parallel bounds to the imaginary axis, which is given here. Not all of them. Yeah, some of them can be retarded. And we also need to look at the so-called strong stability. Yeah, so that to have practical stability of a neutral system, yeah, so it's not enough if the system is stable for nominal delay values, but we also need to take or to look at what happens if the delays are perturbed. Yeah, so then we have this strong stability criterion, which is quite complex in the matrix form, but in the scalar form, it's relatively simple. Yeah, so it's given just, or this gamma zero value is just given by a sum of the coefficients. Yeah, so to look at an example. Yeah, so let's have these three systems: retarded, neutral. Yeah, we have scalar system, retarded, neutral, and classical first order system. Yeah, so as we can see from the step response, yeah, the parameters of the systems are here selected to have this the same dominant behavior, yeah, given by this root Yeah, so of course, time delay models have infinitely many modes, but their influence to the overall dynamics is negligible here. Yeah, so now look at in this neutral system. Yeah, so if you apply strong stability criterion, yeah, so we see that this is not strongly stable. Yeah, because we have 0.6 here plus 0.5 is 1.1, which is larger than 1. So the system is not stable, which is not seen here. Yeah, the step response is fine. Spectrum is also fine, at least on this dominant part. But see what happens if we perturb slightly this delay. Yeah, so the neutral chain is deflected, and in fact we have infinitely many roots entering the right half plane of the complex plane. Yeah, so the system becomes unstable due to high frequency roots. Yeah, so it doesn't matter how small this perturbation is. The smaller it is, then the stability will be lost due to higher frequencies. Okay, so when talking about spectrum of time delay systems, I mustn't forget to mention my algorithm, which I proposed quite long ago at Pavazitek as a PhD student, and developed it to a MATLAB application, which is time to time seen in the references. People are using it probably because it's quite simple to use it, and it's yeah, sort of you have only a couple of parameters to define. But I have to say that it is, or I have to confess that it is suitable for checking spectra of low complexity systems. Yeah, like we see here, yeah, if we have low order time delay systems with several delays, yeah, so we can use it. And also a big disadvantage is that we need to derive the characteristic equation. Yeah, so for having or for solving more complex problems, for example, codes by Bimicheals and Dimitri Breda can be used. Yeah, but try my QPMR algorithm. You can download it from my web, or I can send it to you. Yeah, you see that it's quite simple, the application. Yeah, so let's have this first order neutral system, yeah, with this characteristic equation. Yeah, so it's just very easy task. You can write a function in the MATLAB function form and define the region where you want to compute the roots, and then some additional parameters like grids of the region, which is used for the mapping, and then the desired accuracy. Yeah, so if you want to help with the with the use, just let me know. Okay, so now I come to the main topics of my presentation, and first of them is the delayed resonator. Yeah, so I will first introduce the basic concept, and then I will move from so-called collocated to non-collocated and the multi-dimensional vibration absorption. Delayed resonator concept was proposed in beginning of 90s by Nejat Olgach from University of Connecticut and his colleagues. Yeah, they had plenty of works on this during 90s, and you can also find some works which are relatively recent next to those done by us. Yeah, for example, Alifouad Ergenç work on this topic recently, and I will also mention more this relatively new problem, yeah, which is which is the non-collocated vibration absorption, which is a quite challenging topic. Okay, so let's look at the basic concept or the task which we are solving. Yeah, so we have here a sort of mechanical system which is flexibly connected to the ground. Yeah, so this is the primary mass which is being excited by a harmonic force, a periodic force. And yeah, in mechanical engineering, if you want to suppress vibrations, a typical tool is to use a vibration absorber, yeah, which is mounted here. Usually these absorbers are passive with limited tunability. Yeah, so if you have passive absorber, yeah, so it's tuned for relatively low band of the frequencies. If you want to improve vibration suppression or change or shift the frequency band or extend the applicable frequency band, you can use the active feedback. Yeah, so which is done in this delayed resonator. Yeah, so basically we have a transfer function. You know, we are looking only at the absorber of the isolated absorber with the active feedback. Yeah, so the transfer function looks like this, and we introduce the control action. Yeah, so here, as you will see, we have plenty of options, and some of them is to use an algorithm with a delay. So then the synthesis is relatively straightforward. So we assign a root at j omega, yeah, where omega is the excitation frequency, yeah, frequency of vibration. So we assign the root to the absorber. And then if you look at the transfer function from the excitation force to the position of the platform, which is here, yeah, so the pole of the absorber becomes zero of these transfer functions. Yeah, so which means that we have zero magnitude at this frequency point, and the vibration is fully absorbed. Yeah, so here you see it on the measurements. Yeah, so let's yeah, in the beginning from 0 to 3 seconds. Yeah, so the active feedback was not on. Yeah, so it behaved passively, but it was turned on at time 3 seconds, and you see that the platform position is sort of silence. Yeah, of course, we have some measurement noise at the end, and yeah, the vibrating energy is transferred to the absorber. Yeah, so let me show the first video. You will see this setup in several videos here. Yeah, so we excite the position of this platform, yeah, by the linear magnetic shaker, by voice coil. And this part, yeah, this is the mass of the resonator. Yeah, so here we have another linear motor. Yeah, so maybe I will run it. I will run it again. Yeah, so at the beginning it's yeah, the feedback is not active. Yeah, so we have some shaking of the main platform, but now it was switched on, and even though we still have some excitation here, yeah, so the platform is almost fully silenced. Now let's move to the algorithms, which Nejat, Olgac, and his colleagues used in the delayed resonator feedback. Yeah, so typically they started with position feedback, and then it was extended to position delay feedback. It was extended to velocity delayed feedback, and also to acceleration delayed feedback. Yeah? So you see that the advantage of using this type of control is that it's quite easy to apply. It has two parameters, G and tau. So it can be used to assign the root at the imaginary axis, yeah, the root couple at the frequency j omega, so at the root j omega. When we have position feedback and velocity feedback and couple it with the absorber, the active absorber, yeah, so we have a retarded system. Yeah, so the behavior is relatively safe. But if we do that with the acceleration sensor, which has some advantages, have some practical advantages, we get a neutral system. Yeah, so you see this is the first example that we can really meet neutrality in engineering applications, yeah, the use of acceleration feedback is suitable for mechanical engineering applications because the accelerometers are cheap and they are easy to yeah, it's easy to measure, or it's easy to employ them, yeah, to the system. You don't need to have a reference point like it is as it is usual for position feedback, as you will see in my next presentation. Actually, here in this experiment we used the acceleration sensor here, but later on we moved to position sensor, and it's because of the disadvantage of the accelerometers that it's usually very sensitive to measurement noise. Yeah, so it was partly the reason of the residual vibrations, like residual vibrations, which we could see on the video. Okay, so here, yeah, to remove the neutrality, an option is to employ the distributed delay, yeah, instead of lump delay. Yeah, so it brings some advantages because you see that we take the signal, or make an average of the measurement signal over the period over the delay length. Yeah, actually, this feedback performs the finite impulse response filter task. Yeah, so it takes the average. So it's not that sensitive to the noise anymore, and it removes the neutrality. Yeah, so it turns the neutral problem to a retarded problem. Yeah, of course, yeah, to be precise, yeah, we still have neutral system, but it's degenerate and the spectrum is retarded. Yes, we can nicely see in this Laplace transform form the characteristic function. Yeah, so there is no second power of S delayed. Okay, so let's look at the performance and stability, yeah, of these simple structure delayed feedbacks. Yeah, so because we assign only one root at the imaginary axis, yeah, the perfect vibration suppression is pointwise. Yeah. If we want to look at the robustness, yeah, so from the both diagram, yeah, we see that we can have quite some decay of the performance of the resonator, yeah, when we don't know, yeah, the excitation frequency perfectly, if you have a mismatch between the design and true excitation frequency. Yeah, so this is a disadvantage of these simple structural control rules, delay control rules. And also we have another problem, or we can meet another problem in delayed resonator applications. Yeah, as you may have seen, the design of the delayed resonator is independent of the platform dynamics. So we don't need to have parameters of the platform. Yeah? So this is also one of the advantages, that we only tune the active absorber to the given frequency, and then we can mount it on the vibrating platform, and it should work, provided that the overall system is stable. So what we have done with my colleagues, also with Nejat and my former PhD students, we looked at the stability of the delayed resonator itself, and we have found out that even resonator alone is quite sensitive to the stability. Yeah, so if we have excitation frequency which is smaller than the natural frequency of the absorber, of the passive absorber, yeah, so we can get unstable behavior. Yeah, so this is seen here in this graph, yeah, where we have it shown. Yeah, the stability regions are shown with respect to the damping of the absorber. Okay, so this is shown for LAM delay acceleration feedback, and here we also found out how it looks for distributed delay feedback. And in this paper with Vyhlidal and also Baran Alikoch, you can find similar maps also for velocity and position feedback. And in the graphs, you also see contours of the robustness, which deteriorates when we get quite far from the with the excitation frequency from the passive absorber natural frequency. Yeah, so this best performance of the resonator can be observed in a relatively small region, but still the extension of the applicability of the absorber is substantial. And also, as I have mentioned, we can achieve perfect vibration suppression. Yes, I see that I will need to speed up a bit. So very briefly, I will mention here the works which we have done on extending the robustness. So instead of having this pointwise character of the frequency domain, we can try to attempt to widen it. And in these references, we did it by applying the optimization methods. Yes, you can see here, we employ distributed delay feedback, but with more enhanced or more complex delay distribution. Okay, so it can be pointwise, equally distributed, or even with polynomial distribution. And also in the work by Dantelbauer and Vyhlidal, also the stabilization is involved in the optimization. Then it becomes a nonlinear optimization problem, which we solved by Hanzo tool. In the other works, which are not more recent, but actually this one is actually in review. We use double root assignment. Yeah? So instead of assigning one root at j omega, the imaginary axis, we assign 2 roots, and then the robustness is enhanced, but we need to somehow handle the stability problem. So we use another controller here to stabilize the whole setup. Yeah? So the delayed resonator is used for stabilizing or for suppressing the vibration, and the additional control is used to stabilize the system with the resonator. Okay, so now let me move to non-collocated vibration absorption, which is a recent problem opened by Nejat Olgac. And as you will see, it's the task is more complex. Yes, still we use a delayed resonator. It can be in its very simple form, and but we have a sort of more complex system. Yeah, so here it is assumed to be in a form of serial interconnection of the mechanical oscillators. Yeah, so we are exciting the whole system here from the right by a periodic force, and if you use a classical collocated vibration suppression, yeah, so the task would be to suppress vibrations of this mass m2. Yeah, so the position x2. But for example, if you want to suppress the vibration or absorb the vibration of this mass, yeah, the problem is much more difficult because the still you can see that we have only actuation at the resonator. Yeah, so it needs to exert the mechanical waves, yeah, which ideally suppress the waves coming from the other side. As shown in the work by Nejat, in this serial configuration, we need to define a sort of resonating structure. Yeah, so instead of dealing with the resonator itself, yeah, so we also need to include all these resonating parts and involve them in the dynamics, in the synthesis. And the task is similar, yeah, to the delayed resonator itself, or the collocated delayed resonator. Yeah, so we need to place a root couple at plus minus j omega, but not to the resonator alone, but to the whole structure, yeah, which is a bit more complex, but doable. In Nejat's work, he used acceleration feedback. In our experiment, which is the main result I want to show here, we use position feedback. So this is a bit different, but the synthesis is only slightly adjusted. But as you can guess, we can have some difficulties, yeah, with the stability, yeah, because we basically assign only 1 0 to the system, but when we introduce the time delay, yeah, so it can have quite some destabilizing effect. Yeah, so it doesn't work for any frequency, and the stability problem is open to be solved. Yeah, so in our experimental setup, yeah, so we don't have so many cards yet. Yeah, so many masses connected. We only have 3, and the absorber, yeah, which is mounted to this one. Yeah, so here is M0, M1, and M2. Yeah, the whole structure is being excited, yeah, from the right. Yeah, so we use this voice call to excite the whole system by periodic force. Then this is the absorber, yeah, with the voice coil with the linear motor here. We have here one more linear motor, which is actually not used in this experiment, but we use it in different ones. Yeah, for mainly for stabilization. But now in this experiment, it's not used. So the control algorithm is implemented in LabVIEW. Yeah, so we use this simple position feedback with 2 parameters, G and tau. And yeah, so it's implemented on LabVIEW, and it's run on National Instrument compact trio, yeah, with sampling 1 kilohertz. Okay, so here is the video. Yeah, so we are excited by this voice call. You can see it here, and the first task is to perform the collocated vibration absorption. Yeah, so the task is to stop the motion of this card, yeah, which actually was achieved now. Yeah, so maybe if I run it again. Yeah, so here it's not. Yeah, the suppression is off. Now it was switched to on, and the vibration of the card is really fully suppressed. So let's move to a bit more difficult task. Yeah, so now we want to stop the motion of this middle card. Yeah, so it was actually switched on now. Yeah, so the resonating substructure is not only the absorber but also this card. Yeah, so we are quite. You see some residual motion, but it's always there. Yeah, due to some unmodeled dynamics, yeah, like dry friction and so on. But we believe, or we think that the result is nice. Okay, and now it's the most difficult problem, where we stop the position. This card, yeah, still here we have some the excitation. Yeah, so it did not change, but the card has stopped. Yeah, thanks to the action of the absorber and the wall resonating structure. Yes, and the wave of the opposite force. You may notice that we had to change the frequency. In the first applications, we had the frequency for excitation frequency for 0.5 hertz, but in the last one we had to change it to we had to lower it a bit because for 0.5 it was not stable. Yeah, my PhD student Matěj Kuřa really had together with Jaroslav Bušek, my colleague, really spent a lot of time to get this working, and also to find out the stability regions, which are usually quite narrow. Okay, so what have been done more? Yeah, with Wim Michaels and Heik Silm, and also with our joint PhD student Adrian Saldanha. We looked at a bit more complex problem recently, so which is shown here. So we are targeting our setup model, but notice that here we have another link between the masses 0 and 2. Yeah, so the structure is not fully serial. We have some parallel link, so it means that the resonating substructure cannot be defined so easily or directly, and the synthesis is performed by direct placing the 0 position on the imaginary axis. And meanwhile, we also want to guarantee stability. So therefore, we use additional controller, actually by this voice coil, to achieve stability. So the delayed resonator, in this reference, it's used for assigning the 0, and then we have stabilizing controller. And actually, the 0 assignment doesn't have to be done by delay feedback. So we can use, for example, here classical static output feedback, where the problem is turned to design of MIMO or MIMO system. So we have a system with two control actions, and in the synthesis we assign the zeros, and simultaneously we achieve stable distribution of poles. So what remains to be done on open problems are structural optimization. We currently solve this with my PhD, or we are looking at the problem now with my PhD student Adam Peichel, and it can really help. Yeah, so we were quite lucky that we were able to come with the masses and other parameters of the cards, yeah, to make it working. But if we look at the structural problems, yeah, so much the performance can be much improved. Yeah, so this will come in future. Another task to solve is simultaneous stability and robustness assessment, and of course experimental validation and extension to multi-dimensional case. I really see that time is running quite quickly. Yeah, so multi-dimensional vibration suppression is my following topic. Yeah, so which we looked at with we are working at with my colleague Zbigniew Shika and also Michaels recently. So the idea is to extend the classical concept of one-dimensional delayed resonator to two-dimensional case. Yeah, so if we have for example, platform like this, which can move in 2 degrees or 3 degrees of freedom. Yeah, so it has 3 degrees of freedom, which we have to target. Yeah, so it's planar vibration suppression. Yeah, so next to the motion in X and Y axis, we also have to look at the angular motion of the platform. And as you can guess, it's the extension of the concept is not straightforward, because instead of only one actuation, here we need to have three actuation, and so it's really we come from the single input, single output case to multiple input and output case. Yeah, so first task in the design is to propose an ideal two-dimensional absorber, and its basic feature is that it has unified eigenfrequencies. Yeah, so there are 3 of them, and all of them need to be unified with the excitation frequency. And with Zbigniew Shika and Zdeněk Neuser, we have shown recently that for the given configuration of the absorber or the resonator, it cannot be done only by tuning the parameters. We also have some constraint on the construction. Yeah, so it is shown here. Yeah, so we also need to look at dimensions of the absorber and also the ratio between the mass and the moment of inertia. Okay, so the first step is to design the ideal unifrequency absorber, and then in the next step, by delayed feedback, the physical absorber, which has actually a stiffness and damping in the links, is using these actuators. It is turned to the ideal. Yeah, so it means that the stiffness needs to be virtually modified from the physical to the ideal, and the damping needs to be removed in each of the links. Yeah, so it can be done pointwise for a single frequency, and it can be relatively easily shown that if we do that, so after performing some transfer function analysis of MIMO system, if we assign this unified eigenfrequency, so we have these 3 singular values of the absorber at infinity, and if we observe how the transfer function between the excitation force and the position of the platform looks like, so it's really equal to 0, because here we have the inversion of this matrix. So these terms disappear, and really, the position is equal to 0. So the platform is fully silenced. So here you have just simulation results, which you can find in the reference paper. So in the frequency domain, the synthesis is done by in the spectral domain. The synthesis is done by assigning a triple root at the imaginary axis with the geometrical multiplicity tree. In the frequency domain, the singular values at the frequency. So the excitation frequency is 12 Hertz. Goes to infinity, and for the platform they go to 0. Again, it is pointwise, we can expect that it will be very fragile vibration suppression. Even small reflections between nominal and true excitation frequency will result in substantial decay of vibration suppression. But this is just start of the research. So in time domain, you see here that it was truly achieved. So after switching on the feedback, the platform of silence, and the energy was moved to the resonator. The most recent work on this done by me, Michaels, and Zbigniew Šika, and Zdeněk Neuser, and Jaroslav Bušek, deals with parameter optimization of the absorber. So in the previous work, we just considered that they can be general, but here we show that if they are selected properly, using these rules, so if they are selected properly with respect to the target natural frequency and damping of the absorber, mechanically, the absorber can be decoupled, and then we arrive to design problem, which is identical to one-dimensional delayed resonator. So it very simplifies the synthesis. For example, we don't have 3 delays to deal with; we have only a single delay. So even stability analysis is solved, and we can also easily target the forces and energy which is needed for the design. So what remains to be done is experimental validation. So this is the first setup we have built, or colleagues of Zbigniew, or my colleagues, Zbigniew Šika and his groups at the Department of Mechanical Engineering. So we have built this setup, but there is still some work to do. Because the voice coils, so we use the same structure, the same voice coils, the linear motor, but here they are massive. So and the links mass is quite large, and it's not considered in the design. And also the problem which we handle is with the friction. So this is still open problem on which we will work. And another problem which actually we have recently targeted as well is to extend the delayed resonator from 2-dimensional to 3-dimensional vibration suppression. So in this case, we need six actuators, and in this work, which I only reference, we show which is actually in review, so you will need to wait a bit. hopefully for that, is how to mechanically deal with the design, and it shows that theoretically it's possible. Yeah, it's not that straightforward. It's a quite complex task, but it can be conceptually solved. Yes, so now I will move to the second topic, which as I have mentioned, is very similar, and it's compensation of a periodic disturbance. Actually, motivation for these problems comes from industrial application, which we dealt with in the past, and it is compensation of roll eccentricity in a hot rolling process. So in making the plates, we use these hot rolling mills, which have usually 4 rolls. Yeah, so these 2 are working rolls, and then we have backup rolls, and this backup rolls is controlled by a hydraulic system, and actually by this quantity, which is called the roll gap. We control the thickness of the plate. Sometimes it happens, that we have some unbalanced housing of these rolls, or they have not, or their shape is not circular, it's elliptic. And as a consequence, we have the roll eccentricity, which is projected to the wavy surface of the plate, which needs to be compensated. Another problem which we face here is the relatively long measurement delay, because the control action comes here, but the plate thickness is measured. It cannot be measured directly at the roll position, but it's measured in some distance. Yeah, so it really brings some substantial delay. Classical tool for dealing with the periodic eccentricity, with periodic disturbance, is repetitive control. Yeah, by repetitive control, we can either ideally follow periodic reference, or we can perfectly compensate the periodic disturbance. Yeah, so I will not go too much to the basic concept, which is shown here. Yeah, so here we have the repetitive compensator, which is actually included to the classical feedback loop with the controller and the system. Yeah, and so the sufficient information is only to suppress the oscillations, is to know the period. Yeah, so if we know it, so we include the delay with this period, and if everything goes well, so we suppress the disturbance perfectly. Yeah, so it is done by 0 compensation. Yeah, so here I illustrated on harmonic, this the harmonic functions, but in fact, in this ideal repetitive controller, we have infinitely many roots on the imaginary axis, and if you look at the Fourier expansion of a periodic function, so theoretically we can handle any periodic function. Yeah, so for example, sawtooth or some step-like functions. Yeah, so this is the theory, but in practice we cannot do that, because the spectrum on the imaginary axis is projected to the spectrum of the system, and we have a neutral system with potentially infinitely many roots at the imaginary axis at high frequencies. Yeah, so what is done in practice is that we use a filter in the feedback of the repetitive compensator, but it deteriorates the compensation in high frequencies. there are in literature we can find some works to extend or to design more advanced repetitive controllers which can have more roots on the imaginary axis. But still we can have problem with designing the controller, even if we solve this problem. Because then still we have an infinite dimensional problem, to be solved. Okay, so what as an alternative we proposed to apply this internal model control scheme. So this is done in a classical way, that the controller, actually we assume that the system is described by a first order model plus that time, which we have found out that this model is suitable also for that hot rolling application, from analysis of the measurement data. So what we do, we apply classical synthesis based on the dynamics inversion and employing an additional filter in the controller and additional delay. The filter is structured to gain the feasibility of the control implementation, and also to achieve the pointwise vibration, or this suppression at the point omega d. So the task or the feature to be imposed to the filter is to have a low pass characteristics, which is seen here, but at the frequency omega d it needs to be equal to 1. So this is because in the sensitivity function, which we want to have it to be 0, so the transfer function from d to the output, from the disturbance to the output, so we need to have this term equal to 0. So the first task is to achieve the f magnitude of f equal to 1, and then we need to handle the argument, which is done by this additional delay. So more on the theory it can be found in the conference and the recently submitted paper. And so I will skip to the laboratory experiment, because it's not that easy to find a rolling mill to play with. So we again use our laboratory system, but now we use it in a different way. So it is used to emulate the typical features of the hot milling, and basically it is the long input delay, which is software-wise introduced, and non-oscillatory character. So to gain this, we involve two inner loops in the control. So at the end, if we take the response from the control action to the position x1, which is controlled, so we get this type of step response. Here, actually, this other card is used to excite the lower one by the periodic disturbance. So this actually what we used before as a absorber now is used to excite the system. Again, it's implemented in LabVIEW and run on that compact trio. So this is the first video, which is a bit longer, but I think it's nice and nicely shows how it works. So now it is excited by that by this card. So control action, which comes now from here, is not working, and now it started to work, and really you see that the suppression is excellent. So Jan and Jaroslav did, Jan Yüksel and Jaroslav Bušek did great work, because I didn't expect that it will work so nicely. Yeah, so here you see that it can do the reference tracking. Yeah, so you'll come back to 0, or maybe I will shift it a bit. And recently we have extended this concept, or we have shown that if you extend the feedback a bit, the structure of the loop, you can extend this problem from single frequency to double frequency suppression. Yes, so which is in here. You have a double frequency periodic signal, and again, it can be suppressed. Okay, we have a question here. Maybe I will answer them at the end. Yeah, so it also works. Yeah, and it has features of the reference tracking as well. Yeah, so the only information on the periodic excitation is the frequency. Yeah, so which needs to be known. Yeah, so we don't need to know the amplitude. Okay, so now in the second branch of the this research, we look a bit more complex problem. Yeah, when we have more harmonics, yeah, in the signal. Yeah, so as you can see here, we as a reference for the disturbance, we use sawtooth signal, which is a bit filtered, yeah, by the PD loop, but still looking at the spectrum of the periodic signal, we have 4 dominant frequencies. Yeah, so we use similar approach. Yeah, so again, it's based on internal model control principle, but now we optimize the structure of this distributed delay. Yeah, so we have a distributed delay here, and we can also have another filter to gain the feasibility, or actually it doesn't have to be here at all. Yeah, so we can only have the distributed delay, and that's it. Yeah, in the controller. So these gains are parameters to be tuned. Delays are assumed to be known. Yeah, so this and the synthesis is now done by robust design. Yeah, so we minimize the weighted sensitivity function under some given constraints. Yeah, so we use the same setup as before, and the constraints are used mainly, yeah, to assign the dominant the zeros or the roots of the distributed delay on the imaginary axis, yeah, at the frequencies to be targeted, and also there are some additional structural constraints to be fulfilled, and we can also involve some inequalities. For example, if you want to limit the jerks, yeah, of the control actions. Yeah, and the synthesis is done by a robust frequency domain synthesis H infinity by minimizing the weighted H infinity norm. Yeah, so these are results which show that it works. Yeah, really, even though if we have this quite nasty periodic signal, yeah, it works surprisingly well. And this is the video taken by Jan Yüksel. Yeah, so to see it a bit more distinctly. Yeah, so from now the video is slowed down. So you see that how this motion of this card projects to the motion of this card. And actually now, yeah, the feedback starts operating, and you see that it almost does not move this card. Yeah, so it works very nicely, we think. Okay, so I see that I'm running out of time. Yeah, sorry for this. Gabor, can I have 5 minutes more?
Sure. Yeah,
sure, yeah,
I think you have some nice things at the end. Some.
Okay, so this is only a note, because I knew that it's too much to put to one presentation, but I think these are nice. Mainly the experimental results which I have at the end of the presentation are nice. So I included also this topic, input shaping. And again, a bit theory, but mainly experimental validation. Yeah, so input shaping is a different problem. Yeah, so it's not vibration suppression, flexible mode compensation. Yeah, so it was shown here that if we have a card, yeah, with a suspended pendulum, yeah, and we move with the card from one position to the other, yeah, so we have oscillations of the pendulum. Yeah, so to precompensate, yeah, the oscillations, we can use input shapers. Yeah, so it was done here. Yeah, so the reference was filtered by an input shaper, and as you can see, yeah, we have almost no oscillations at the end. Yeah, this concept is used a lot in, yeah, mainly in crane applications, and also in some flexible robotics. It's yeah, the theory, yeah, and the use of input shapers is quite or the problem is has been handled for quite a long time. Yeah, the first Otto Smith worked on it, yeah, in the 50s, late 50s. Yeah, he proposed a sort of posicast controller or compensator, which is actually exactly the same very basic input shaper which was in the 90s targeted by the group of Singer Searing and then Singhaus in MIT. Maybe we see very big gap between the 60s and the 90s. Yeah, we don't have too much works on this, almost none, I would say. Yeah, it was perhaps because it was not easy to implement controllers on using analog circuits. Yeah, so but as soon as a digital control came into action, yeah, so implementation delay become very easy, and the potential was recognized. Yeah, so very shortly, yeah, so we have a system with some flexible mode, which can be represented by this complex root couple. Yeah, so if we know the root, yeah, so we can easily design a shaper, yeah, which is put into the series before the system. Yeah, so the input shaper, the very basic ZV shaper, looks like this. Yeah, so it's only weights the non-delayed and delayed control, the delayed input. Yeah, and then if we do it properly, yeah, the delay is related to the oscillation period and the damping of oscillations. If we do it properly, yeah, in the step response, you know, the oscillations are perfectly compensated. Yeah, the reaction to the second step compensates the reactions to the first step. And if you look at it in the spectral domains, so we have again zero pole compensation. But you see that if you use this type of shaper, we have a neutral spectrum, which can be dangerous in some practical applications. So what we have done as our first work in input shaping already a long time ago, so we substituted the lump delay by a distributed delay. So instead of two steps, we have a step and a ramp signal. So the behavior is a bit smoother, or the responses are a bit smoother, but on the other hand, they are a bit longer. But it works. Again, similarly to vibration suppression by delayed resonator, if you have this single root assignment on the imaginary axis, we have quite high fragility to the mismatch between nominal and true frequency of the flexible mode. So in literature, you may find a lot of robust alternatives of the shaper. Typically the structure is extended to this multi-delay problem, and we can have, for example, zero vibration derivative. So if we assign a double root at the flexible mode, or this extra insensitive shaper. So we really, so these are residual. This is magnitude of the residual vibrations which we can observe if you have a mismatch between nominal and true frequency. Okay, so a very brief note what we have done on this topic. So again, we played a bit more with the distributed delay. So we have designed the robust alternatives of those classical input shapers. Again, the advantage is a smoother behavior, and also we address some stability issues. And once in this last fork, which we had with our colleagues from University of Pilsner, Martin Goubey and Miloš Legl, so we also imposed some frequency domain filtering issue, which you will see in the following slide. But here we did not target it, the distributed delay, but discretized lump delay. But the problem is very similar and can be handled by analogous approaches. So here we have the result. So the system to be, unfortunately, I don't have a video for this one. So this is again some flexible beam, rotating flexible beam, and this is the comparison between the classical double zero vibration derivative shaper and the shaper which was designed by the optimization method. So this is this purple one. So instead of series of jumps, we have a smooth signal, and interestingly, it is of the same length. So which is an important improvement. And also in the frequency domain, we filter out the higher frequencies. So what I want to show in the last video is not that complex problem if you look at the design, because often in industry, if you come with some very sophisticated control structure, compensator structure, so they will tell you that it's not possible, that the implementation needs to be done in a cheap way, and it needs to be reliable, and with the complexity, of course, this can be endangered. So this therefore we came with some intuitive approach. So again, the task was to design a input shaper for a crane application. You will see it in a video, which is the last one. And the task was to have some robustness against the mismatch between the ideal and true behavior of the flexible part, and also to respect the constraints, the limits of the actuator, which is concerning the velocity of motion. So we have some constraint on velocity, acceleration, and also jerk. So what we did is that we used a classical extra insensitive shaper, and which actually would provide impulse-like or stepwise functions. So all these constraints would not be fulfilled, and we included a pre-shaper. So a function by which we impose all the constraints. So at the end we have a control action, which is relatively easy to implement, and it has some robustness and also fulfills the predefined constraints. So here you see application, which is in steel industry. So it's material. This is a technology for material hardening. So this is the furnace from which you have to take the plate, and here we place it on the conveyor belt. And as you may have noticed, so we observe almost no oscillations, or oscillations at high frequencies. So if there was no that input shaper, the behavior would be similar to my introductory video. So it works fine. And at the last slide, it is maybe more interesting. So it's operating. So we have a furnace for heating the material, and now it's put to the chilling chamber. Okay, and it works also here. So this is all. I apologize very much for taking so much time, but thank you that you stayed so long, and thank you for attention, and of course many thanks to my collaborators from the department, Jaroslav Bušek, Jaromír Fischer, Milan Anderle, Petr Denke, Jaroslav, Milan, Peter. They had a lot on the implementation of this laboratory setups. Also together with my PhD student Matěj, Jan did nice work on that periodic vibration suppression. You may see a reference to work of Adrian. And Adam also work on structural design of non-collocated problem. And of course, from CTU, I thank to my colleagues, collaborators, closest collaborators on this topic, Zbigněk Šika, Martin Romčík, Sergej, and of course, I have to thank to Mikels, Nejat Olgač, Silviu Niculescu for collaboration. Also, recently we started collaboration with Tarun Singh, also a big name of input shaping. And I thank also to industrial partners, PTSV and ZAT, and of course for the budget providers, Czech Science Foundation, Technology Agency, Ministry of Education. So it's all from my side. Thank you.
Thank you very much, Tomas, for this very nice talk.